Right now, somewhere on Earth, a machine is helping manufacture the processor that will power a future iPhone, train an artificial intelligence model, or guide a satellite through space. Without that machine, technological progress doesn't stop, it slows. And the extraordinary part is that only one company on Earth knows how to build it. You've probably never heard its name. ASML. It doesn't make smartphones, design computer chips, or operate social media platforms. Yet companies worth trillions of dollars quietly plan their futures around its ability to deliver a single machine. Apple depends on it. Nvidia depends on it. TSMC depends on it. Even governments have reshaped foreign policy because of it. Few businesses operate so quietly while influencing so much of the modern world. How did an obscure Dutch company become one of the most strategically important businesses on Earth? The obvious answer is that ASML invented an extraordinary machine, but that's only part of the story. Its real advantage was never the machine itself. It was something far more difficult to build and almost impossible to copy. To understand why, we need to go back to 1984, when ASML wasn't an industrial giant. It was a small spin-off from Philips with little money, almost no reputation, and virtually no reason to believe it would ever challenge the established leaders of the semiconductor industry. They had decades of experience, superior technology, and manufacturing capabilities that seemed impossible to match. Against competitors like these, ASML looked less like a future champion and more like another ambitious startup destined to disappear. Almost everyone believed the winners had already been decided. ASML believed the game itself could be changed. By the mid-1980s, the semiconductor race already seemed over. Japan wasn't simply leading it, had built an industrial powerhouse. Companies like Canon and Nikon dominated lithography through decades of relentless engineering, manufacturing discipline, and continuous innovation. Against competitors like these, ASML couldn't win by building a slightly better machine. Playing the same game would only guarantee that it stayed permanently behind. If the company wanted to survive, it needed something far more ambitious. It had to leap beyond the industry's roadmap, and that leap had a name. Extreme ultraviolet lithography, or simply EUV. The promise was extraordinary. EUV could print circuits so small that computing power could continue advancing long after existing technology reached its physical limits. There was just one problem: many of the world's leading experts believed it couldn't be done. Extreme ultraviolet light is almost impossible to control. Ordinary lenses absorb it. Even air blocks it. A working machine would require mirrors polished with atomic precision, an entirely new light source, and a vacuum environment unlike anything ever used in commercial manufacturing. ASML wasn't trying to build a better product. It was attempting to solve a chain of engineering problems that had never been solved together. Every breakthrough depended on another breakthrough. Better optics required better manufacturing. Better manufacturing required better materials. Better materials demanded entirely new levels of precision. It wasn't one impossible challenge, it was dozens happening at the same time. Years passed, deadlines slipped, budgets grew. Prototype after prototype failed to meet expectations. To outsiders, the project looked less like innovation and more like an expensive experiment refusing to die. Inside ASML, however, every failure carried the same message. They weren't proving the idea was impossible, they were discovering one more way it wouldn't work. By the early 1990s, ASML had spent years chasing EUV with almost nothing to show for it. The technical obstacles kept multiplying, investors grew impatient, and competitors watched from a safe distance, convinced the project would eventually collapse. From the outside, that conclusion seemed perfectly reasonable. Inside ASML, it produced the opposite reaction. Engineers like Martin van den Brink believed the company wasn't trying to improve lithography, it was trying to reinvent it. If the industry wanted another incremental step, ASML would lose. But if the future demanded a technological leap, there was still a chance. That belief came at an extraordinary cost. Every year required more money, more experiments, and more patience. Suppliers were asked to build components for a machine that didn't yet exist. Customers wanted results, shareholders wanted certainty, and no one could promise either. Most companies would have accepted reality. They would have canceled the project, written off the losses, and returned to safer ideas. ASML reached the opposite conclusion. Walking away wouldn't save the company, it would guarantee irrelevance. So they kept building, refining, testing, and failing again. not because success was becoming more likely, but because it was becoming more necessary. Eventually, however, persistence met a limit that engineering couldn't overcome: money. No matter how talented the team, no company could finance an experiment of this scale forever. The greatest threat to ASML was no longer engineering, it was survival. Developing EUV demanded an amount of money that no company could justify spending forever. Every delay consumed more capital. Every failed prototype tested the patience of investors. Eventually, persistence alone would no longer be enough. If nothing changed, one of the most ambitious engineering projects in history would simply run out of time. Then something happened that had never happened before. The companies expected to buy ASML's machines decided they would help build them instead. In 2012, Intel announced it would invest billions of dollars in ASML. Soon after, Samsung and TSMC followed. Three fierce competitors had independently reached the same conclusion. If EUV failed, everyone would lose. At first, the decision seemed almost irrational. Why would rivals finance the same supplier? The answer changes everything you think you know about ASML. By then, the challenge had grown far beyond building a single machine. Every advance depended on dozens of breakthroughs happening at exactly the right time. A better laser meant nothing without better mirrors. Better mirrors meant nothing without more precise mechanics. More precise mechanics meant nothing without new software, new materials, and manufacturing tolerances measured in atoms. No company, not even Intel, could solve every problem alone. ASML's greatest invention wasn't the machine, it was the system that made the machine possible. Instead of mastering every technology itself, ASML became the company that connected the world's best specialists. ZISS perfected mirrors so smooth that their imperfections were measured in fractions of a nanometer. Cymer pushed laser technology beyond what most engineers thought commercially possible. Hundreds of suppliers solved problems that had never existed before. Each breakthrough strengthened every other breakthrough. With every passing year, copying ASML became exponentially harder. Competitors weren't falling behind because they lacked money or talent. They were falling behind because rebuilding an entire ecosystem is far more difficult than copying a product. When the first commercial EUV machines entered production, the industry celebrated an engineering miracle. What it had actually witnessed was the birth of a monopoly built not on patents or price, but on complexity. The industry's biggest question changed overnight. It was no longer, can this technology work? It became, who can get access to it? Every advanced processor powering artificial intelligence, cloud computing, autonomous vehicles, and modern smartphones now depends on manufacturing techniques made possible by EUV. Companies like Apple, NVIDIA, AMD, and Qualcomm design the chips. Manufacturers like TSMC, Samsung, and Intel produce them. But every one of them begins at the same place: an ASML machine. Almost without anyone noticing, the global technology industry had developed a single point of failure. That realization transformed ASML from an engineering company into a strategic asset. Governments no longer viewed semiconductor manufacturing as just another industrial sector. It had become the foundation of economic growth, military capability, and technological leadership. Whoever controlled access to the world's most advanced chips would influence the next generation of artificial intelligence, communications, defense systems, and scientific research. Business had become geopolitics. No country understood that challenge more urgently than China. For years, Beijing invested hundreds of billions of dollars to build a world-class semiconductor industry. New fabrication plants appeared across the country. Top engineers were recruited from abroad. Entire national strategies were designed around reducing dependence on foreign technology. Yet one obstacle refused to disappear. Without access to ASML's most advanced EUV systems, producing cutting-edge chips at the same level as global leaders became dramatically more difficult. As export restrictions tightened, a commercial machine evolved into one of the world's most valuable strategic technologies. For perhaps the first time in modern history, a private company had become an essential player in the balance of power between nations. The question was no longer whether ASML had changed the semiconductor industry. It was whether the world had become too dependent on a company that almost nobody knew existed. History has a way of humbling every technological giant. IBM once defined computing. Kodak owned photography. Nokia dominated mobile phones. Each seemed impossible to replace until the world changed. Could the same happen to ASML? It's a question investors, competitors, and governments are all asking, because history rarely allows a leader to remain untouchable forever. ASML is already preparing for that future. Its newest generation of machines, known as High-NA EUV, pushes manufacturing to an even greater level of precision, allowing engineers to produce chips that only a few years ago existed only in research papers. Every system contains hundreds of thousands of components, takes years to develop and assemble, and operates with engineering tolerances measured on an atomic scale. The technological gap continues to grow. But history teaches another lesson: no monopoly is permanent. Around the world, governments are investing billions to strengthen their own semiconductor industries. China continues searching for alternatives. Researchers are exploring entirely new manufacturing techniques that could one day bypass today's lithography altogether. Whether those efforts succeed remains impossible to know. What is already certain is that ASML changed the rules of industrial competition. Its greatest achievement was never building the world's most advanced machine. It was building an ecosystem so complex that the machine became almost impossible to separate from the network that created it. The product can be studied. Individual technologies can eventually be replicated, but reproducing decades of accumulated expertise across hundreds of specialized partners is an entirely different challenge. That's why ASML isn't simply another successful company, it is infrastructure, invisible to most people, essential to everyone. Every breakthrough in artificial intelligence, every faster smartphone, and every more powerful processor begins long before consumers ever see the finished product. It begins inside factories that almost no one will ever visit, using machines built by a company that most people will never recognize. That's the hidden ledger. History usually celebrates the companies in the spotlight, but civilization is often shaped by the companies working just outside it.